Hello students, welcome back from the weekend. A few things just to get us started. One, I'm obviously not able to be here today, but I should be back on Wednesday. Two, I'm sort of in the process of getting through a cold right now, so I apologize in advance if my voice is coming through nasally. I can hear it right now, and well, it is what it is. Third, since we're in sort of the swing of things to some degree as the semester's going on, we've regulated our schedule to the degree that the homework, which is going to be assigned from the content of today and tomorrow's class, well, actually, we don't have class tomorrow. The content of today and Wednesday's class is going to be due on Thursday at 9:59. This is the standard way that we're working through things. Yeah, ultimately, you'll be able to get a jump start on this assignment based off what we covered today. So, where we're going to be heading today is, in particular, to continue off of what we were discussing at the end of class on Friday. And if you recall, we were talking about how the act of adding fractions and using a common denominator can be applied to situations even when you're encountering variables. So let's just sort of roll through an example to see this in action. But ultimately, let's say we were trying to add 10 over x minus 1 minus 1 over x plus 3. Now, as you know, anytime you're adding fractions, you're going to need a common denominator. And with numbers, you like to work with the numbers and sensitively find the least of the common multiples to make your computation as simple as possible. Well, in some sense, whenever you have the variables, it's more difficult to go through such a process because it's hard to know the divisibility relations between x minus 1 and x plus 3 in particular. So how can we go about it? Well, a simple way to find a common multiple of any two numbers is to just multiply those two numbers together. So, because heck, if you take x minus 1 times x plus 3, you certainly have a multiple of x minus 1 because x minus 1 is a factor of that. Just as well, if you take x minus 1 times x plus 3 is a factor of that. So let's use that to guide our thinking. So by taking the denominators, multiplying them together, we'll get a denominator of x minus 1, x plus 3. And that denominator now is a multiple of each of the original denominators, but a denominator that's in common, which is now going to allow us to add the fractions. So we simply have to look at each of the fractions that we had and say, okay, what do we need to multiply by to get us from the original form of the fraction to the form that we're looking at with the common denominator? Well, of course, in the case of the first fraction, we have the x minus 1 factor already. We need the x plus 3 factor. So we're going to multiply the top and the bottom of that first fraction by x plus 3. Why the top and the bottom? Well, of course, if you just multiply the bottom, you throw off the value of the fraction. When you multiply by top and bottom by any number, you're really just multiplying by 1, which is giving you a fraction of same value in return. So downstairs, we'll get the x minus 1, x plus 3 that we have written there. Upstairs, we'll get 10 times x plus 3. What about on the second fraction? The second fraction, we've got the factor of x plus 3 already expressed, and we simply need the factor of x minus 1. So we'll multiply top and bottom by x minus 1, again, because multiplying by anything over itself is like multiplying by 1. Downstairs, we'll get the common denominator of interest, and upstairs, we will get 1 times x minus 1. Now, how do we proceed from here? Well, since we've got a common denominator, we just work with the numerators, because we're dealing with sort of pie pieces of equal size now, and we simply just have to add the values that are in the numerator, or in this case, I suppose, subtract them. Okay, so how are we going to do that? Well, just taking a look at the values that we've got upstairs, like in this first guy, we've got a 10x plus 30, taking the 10 and distributing it to the x plus 3, taking the 1, distributing it to the x minus 1, we have the x minus 1. Okay, now we've got to take the 10x plus 30 and subtract the x minus 1. So in particular, that's going to look like this. 10x plus 30, subtract x minus 1. Note, in particular, we have to subtract all of the x minus 1. Since this entire fraction on the right is being subtracted, we have to subtract every part of that fraction. The denominator is, of course, the common denominator of x plus 1, x plus 3. And in one step now, we'll be able to polish off the problem by doing the subtraction. So combining like terms upstairs, we've got 10x minus an x. Well, of course, taking an x away from 10 would give you 9 of those x's. And then numerically here, we've got a 30 minus a negative 1. So in particular, note when we distribute the minus to the minus 1, that's going to be a plus 1. So 30 plus 1, 31. Problem solved. So again, adding fractions, totally possible, even in the case where you're working with variables. Just to get us extra familiar, let's roll through an additional example. So this is going to look fairly similar, but just to get ourselves comfortable with this process, because processes like this come up relatively frequently. So this problem, we're adding 3 and x over x plus 2. Now when you look at this problem, on the surface you say, whoa, how are we going to add these two things? They're not even both fractions. Well, of course, any number which is not a fraction could be a fraction if you simply wrote it over 1. The fraction bar means division, and of course 3 divided by 1, well, anything divided by 1 is just that anything. So if we write 3 as 3 over 1, we're putting ourselves in a position where it looks like, more so, we're adding fractions. So then you say, okay, what is the common denominator going to be here? Well, we can follow the same strategy that we followed in the previous problem. When you're dealing with these terms involving variables, it's difficult to understand the divisibility relationships and sort of sensitively work your way to a common denominator. So the sort of the easiest way to do it is just to match the numbers together and say, okay, take 1, take x plus 2, multiply them together, that's going to be our common denominator. So we want our first fraction to be over x plus 2, and we want our second fraction to be over x plus 2. Well, in fact, the second fraction is already over x plus 2, because the second fraction was originally written as such. Excuse me. We simply have to take the first fraction and get it to be a denominator over x plus 2. Well, how are we going to do that? Well, we got to multiply 1 by something to get to x plus 2. Well, that's going to be multiplying by x plus 2. What we do downstairs, we have to do upstairs, so that in effect, we are multiplying by 1. Downstairs, 1 times x plus 2 gives us the denominator we were after. Upstairs, we get 3 times x plus 2. Altogether, what does this say? Well, this is all over a fraction of x plus 2, and upstairs we've got what? 3x plus 6 plus x. In some sense, no sweat at this point. Since we're just adding, that's easier than subtracting, in the sense that whenever you're subtracting, you have to account for the subtraction sign. Here, the thing that we're adding, in fact, we're only adding one thing, so nothing too difficult here. So combining like terms up top, 3x plus x is going to give you a total of 4x, and then we still have the plus 6. And this is all over x plus 2. And again, as we did with the last problem, and as we did here, you can see that in spite of the fact that we're dealing with fractions of variables, you can still add them. Just like whenever you're adding and subtracting expressions that don't involve variables, you get a common denominator. Once you get a common denominator, you're dealing with pi pieces of the same size, and then you can just add the pi pieces, in particular, add the numerator values. Okay, so with adding fractions sort of under our belt, let's switch gears a little bit to dealing with multiplying and dividing. Now, multiplying and dividing fractions, I mentioned this on Friday, is in some sense simpler than adding fractions. Adding fractions, you need a common denominator. When you multiply fractions, life is not too difficult. If you have a fraction a over b times c over d, you just multiply top by top, bottom by bottom. So you multiply the a and the c, you multiply the b and the d, and you have your solution. Now, dividing fractions is a little bit more complicated, but only slightly. Here's the idea whenever you divide fractions. If you had a over b divided by c over d, well, the way in which we approach this, or the way in which this can be approached at least, is to make a recognition of the fact that division and multiplication are very linked. I mean, one is just the inverse operation of the other. So when you are dividing by the fraction c over d, this is identical to if you were multiplying by that fraction flipped. Division is the inverse operation to multiplication, so division by a fraction, you could multiply by the inverse. Multiply by d over c instead of dividing by c over d. But now that you're multiplying, you just go top by top, bottom by bottom. AD over BC. Okay, so now as I write that out, you might think to yourself with some skepticism, does this property that I've described as to dividing by a fraction and multiplying by its inverse make sense even beyond that? Let me just run through a couple thoughts here, just so that this can make sense in your mind. I mean, what if you took some number, like 20, and divided it by 2? Now you know what the effect of division by 2 is. But think about it. 2 could be thought of as 2 over 1. And my claim is, and I think you should agree with me, that if instead of dividing by 2 over 1, you multiply by a half, that's going to do the same thing. Because anything divided by 2 is the same as that anything multiplied by a half. The act of multiplying by a half is the same as dividing by 2. I mean, hell, divide by 3. The act of dividing by 3 is the same as multiplying by a third. But a third is just the inverse of 3 over 1. So, long story short is, this idea of dividing fractions as being multiplying by the inverse makes nice sense, even in examples like that where we're looking at it just to sort of get a feel for the idea. Okay, so what can we do with this? So as an example to see this sort of in full view, let me give you an example here to see this in action. So let's say x squared plus 5x plus 6 over x squared minus 3x minus 4, and we are going to divide this by x squared minus 4 over x minus 4. And ultimately here, the process here is going to be to divide and simplify. So, looking at this problem, how can we proceed? Now, as you look at this, you might say, well, oh, we've got an x squared over an x squared. Those two things are going to cancel. If you thought that, I mean, that's not an unreasonable thought on one hand, but I claim that that's sort of violating the laws of math. Because look at what is upstairs and downstairs in this fraction. You've got x squared plus 5x plus 6. Downstairs, x squared minus 3x minus 4. Upstairs and downstairs, we have statements based on addition and subtraction. Now, what does a fraction bar mean? A fraction bar means division, right? 12 over 4 is 3. 15 over 5 is 3. 20 over 2 is 10. The fraction bar means division. Does division undo addition and subtraction? Well, no, it doesn't, right? Division only undoes multiplication. So if we want to cancel across a fraction bar, if we want to cancel using the operation of division, we're going to need statements on top and bottom that involve multiplication. Can we do that? Can we take expressions involving addition and subtraction and make them statements involving multiplication? Well, hell yeah, right? I mean, that's what we did last week when we talked about factoring. So let's take each of these terms, like each of these upstairs, downstairs parts of the fraction, and let's write them in factored form so that we can exploit the relationship between division and multiplication. So, x squared plus 5x plus 6, we can factor that, right? Because anytime you're factoring an expression of the form ax squared plus bx plus c, which this certainly is, we can just simply find two numbers that add to 5 and multiply to 6 times 1 in this case, which is just 6. Okay, what two numbers multiply to be 6 but add to 5? That is 2 and 3. What can we do with the 2 and the 3? The 2 and the 3, we can break apart our 5x term into a pair of terms, x squared plus 2x plus 3x plus 6. Having broken that single term into a pair of terms, now we have 4 terms that we can factor by grouping. The first 2 terms have an x in common. The second 2 terms have a 3 in common. And upon factoring that out, you can see how this factors. X plus 3, x plus 2. All right, what about downstairs in the fraction? Downstairs we've got x squared minus 3x minus 4. Wouldn't it be nice if that was expressed in factored form to exploit the cancellation property between multiplication of the factored form and the fraction bar being division? Well, let's write that downstairs expression, x squared minus 3x minus 4, in factored form. So how can we factor? Well, as we always do with expressions of the form ax squared plus bx plus c, we need 2 numbers that add to minus 3 and multiply to a times c, which is minus 4 in this case. Okay, what are those numbers? Well, multiplying to minus 4, adding to minus 3, looks like that's going to be minus 4 and 1. And rewriting then the middle term as a pair of terms using these 2 numbers, we can go x squared minus 4x plus x minus 4. With 4 terms now, we can factor by grouping 2 at a time. The first 2 terms have an x in common. The last 2 terms have only a 1 in common. Both now have an x minus 4 in common, and what? We get x plus 1, x minus 4. Look at the second fraction, the fraction that's being divided away, the x squared minus 4 and the x minus 4. Now you know that the x minus 4 can't factor because it's already something of degree 1. What about the x squared minus 4? Well, the x squared minus 4 is something with 2 terms. That's actually one of our special cases. So in particular, you could write that as x squared minus 2 squared, and then you have a difference of squares. That one, as we saw on Friday, you take the first plus the second, and then the first minus the second. So x plus 2, x minus 2, and now we have a factored form for that. So here's what we're going to do. We're going to take these factored forms and put them into our expression. So instead of writing x squared plus 5x plus 6, we're going to write x plus 3, x plus 2. Because x squared plus 5x plus 6 is equal to x plus 3 times x plus 2. But now we've got a multiplication statement which allows us to cancel. What about x squared minus 3x minus 4? That guy we computed to be x plus 1 times x minus 4. And then we divide. Well, hell, actually, as I'm writing out this division, you know how to divide fractions. Instead of dividing by this fraction, you know division, the inverse operation of multiplication, you could simply multiply by the inverse. So let's do that. Instead of dividing by this fraction, let's multiply by the inverse. So let's take the x minus 4 and put it upstairs, and take the x squared minus 4 and put it downstairs. The x squared minus 4 we factored to be x plus 2. X minus 2. And now what you see is, we've got a bunch of things upstairs being multiplied, a bunch of things downstairs being multiplied, with a fraction bar in between. X plus 3 times x plus 2 times x minus 4, and this times that, times this, times that. And the multiplication now, undone by the fraction bar, which means division, we can cancel on top and bottom. So the x plus 4 that's being divided away downstairs will cancel with the x minus 4 will cancel with the x minus 4 that's upstairs. The x plus 2 that's upstairs will cancel with the x plus 2 that's downstairs, because an x plus 2 multiplied and an x plus 2 divided will cancel. Nothing else is going to cancel here because we have no other common factors on top and bottom, and all we have left then is x plus 3 over x plus 1, x minus 2. sorry for that brief interruption. I was just checking the time to make sure that we're, like the time we've got left. So, okay, so we've gone through an act of dividing fractions, of multiplying fractions in effect, because anytime you're dividing fractions, you really just flip and multiply. What about another particular case? Because we saw whenever you have two fractions divided, written horizontally, what if you had two fractions? This is another example of division. What if you had two fractions that were written vertically? What if you had A over B over C over D? This type of compound fraction can be sort of intimidating looking on the surface. But if you think of it as, okay, what does a fraction bar mean? A fraction bar means division. Well then, instead of writing this thing vertically, you could very easily just write this thing horizontally. A over B divided by C over D could be written horizontally. A over B divided by C over D. And of course you know how to deal with this. Anytime you're dividing fractions, you could just multiply by the inverse. So instead of dividing by C over D, multiply by D over C. And of course then you could simplify this out to be AD over BC. But the long story short is, anytime you have a fraction over a fraction, you could rewrite it horizontally and in some sense make it easier to process. So what if we had something like this, just to see in action the property that we've described here. What if we had something like x over y plus 1 divided by 1 minus y over x. Here's a situation where we have fractions over fractions. Well, I guess not technically yet, because we don't exactly have this form, fraction over fraction. Upstairs we've got an addition statement, downstairs we've got a subtraction statement. But if we could take what's upstairs and downstairs, use a common denominator to add that together, we could get upstairs as a single fraction, downstairs as a single fraction, and then put us in a position where we just have to divide the fractions. So let's do that. Upstairs, to add, we need a common denominator. We have a denominator of y. Let's write both of the terms upstairs as a fraction over y. Remember, 1 you could think of as 1 over 1, and then to get that common denominator of y, you just multiply top and bottom by y. So upstairs we have x over y plus y over y. Downstairs, we have a denominator of x. To get a denominator of x from something that has no denominator or has a denominator of 1, just multiply by x, right? Multiply by whatever that thing is, and now x over x is 1, right? So x over x minus y over x. To simplify this further, combine over a single denominator. Upstairs we have x plus y all over y. Downstairs, each fractions over x, we just have x minus y over x. It took a little bit of working to add together upstairs and downstairs, but once we did, we have it in precisely the form that we talked about, where we have a combination fraction. A fraction over another fraction. Intimidating as it may look, interpret the fraction bar in between as division, and all you have is x plus y over y divided by what's downstairs. But you know how to work with division of fractions. Multiplication, the inverse operation to division, just multiply by the inverse. And now, we've got x plus y times y upstairs. That's a multiplicative statement, which division will cancel. Downstairs, we've got y times x minus y. That also is a multiplicative statement, which will cancel excuse me, across the fraction bar. So in particular, because we've got a factor of y upstairs and a factor of y downstairs, multiply in a y, divide out a y, that's going to cancel. And what we're going to be left with is just x plus y, x minus y. Now, if you want to cancel here the x's, you've got to remind yourself, what do we have upstairs? I mean, read what's upstairs in this fraction to yourself. X plus y plus. We have an additive statement upstairs, downstairs, x minus y. Subtraction. Is addition or subtraction canceled by division? The answer is no. The only thing that division cancels is multiplication. So since we've got an additive statement up top and an additive statement down below, that's not going to be canceled by division, and this is the best that we can do. And long story short, on the idea that was really at play in this problem is, if you are in a situation where you have a fraction over a fraction, complicated as that may look on the surface, if you write it out horizontally, it's really not all that bad. Just keep in mind that the fraction bar in between is division. And when you do, you're sort of one step away from re-expressing the statement in a form that's going to be easier to process. Okay, so that rounds out our discussion of fractions involving variables. We dealt with addition and subtraction, we dealt with multiplication and division. These are processes that we're going to use a lot, because we're going to see fractions, we're going to see variables. We need to know how to add and subtract using a common denominator. We need to know how to multiply and divide like we've seen here. But now turning the page into section 1.5, we are going to introduce talking about one of the most important objects, and frankly all of math, which are equations. Now when we talk about equations, you almost see a mathematical word in the word equation. And you almost see the word equal. And in fact, equations are just mathematical statements with equal signs. That's it. That's all an equation is. And in fact, I claim you have seen equations dating back to like early in elementary school. When you have something plus 4 equals 6, of course you know that something is 2, but the idea is this is a mathematical statement with an equal sign. There's a point in your studies of math where you took the venture from boxes to letters, but the idea is exactly the same. The box represents something that you don't know yet, as does the variable. If we knew what the variable was, we wouldn't write it as x, we'd write it as what it is, just like if we knew what the box was, we would write that in. Okay, now, certainly equations like this are simple, but you know, why on some level is this equation simple? One way to like look at this equation and say, okay, this equation is simpler than this equation. What makes the equation x plus 4 equals 6 simpler than x squared plus 5x plus 6 equals 0? Well, on one hand, when you look at the variable that you're working with, x, this variable here is only to degree 1, whereas this variable here is to degree 2. Degree 1 is certainly simpler than degree 2. You have less going on mathematically in the case where the variable is just stated as opposed to stated times itself. Any equation that's of degree 1 we refer to as a linear equation. Now why we refer to it as a linear equation may not exactly be clear just yet, but I guess in particular if you think back to your mathematical past, you've probably encountered the equation of a line, y equals mx plus b. M and b are just numbers. Note x and y of degree 1, linear. Excuse me. When you have expressions of degree 2, equations of degree 2, when your variable is to degree 2, we call these equations quadratic. So today, we're going to experience like a simple version of a linear equation, simple version of a quadratic equation, things that you've seen before, to ultimately set the stage for studying more complicated versions of both, as well as versions even more complicated than just linear and quadratic equations. So here's one fact about linear equations. What makes linear equations simple is that you can solve directly. What I mean to say by that is you can go right after isolating the variable of interest and solve directly. These quadratic equations like can require indirect methods. We'll see examples of that as we sort of proceed. But for today, let's just sort of get our sort of mental wheels rolling in the direction of thinking about equations. So let's deal with an example. And this example is going to be a linear example. A linear example you can solve directly. Here's one, let's go 7x minus 4 equals 3x plus 8. As I mentioned, this is linear. I mean, you wouldn't necessarily be told in advance that an equation is linear. You'd simply be asked to solve for x. When we want to solve for a variable, we want to find out what values for x make this equation true. Because, for example, if you just plugged in x equals 0, you'd get minus 4 equals 8. That's not true. So x equals 0 doesn't solve this expression. Whereas, like, you know, there might be a particular value of x if we plugged in would make this equation true. So the question is, what values of x would make this true? We've got the linear equation because the variable x that we're trying to solve for is only of degree 1. And my claim is you can solve that directly. Put every x term on one side, put everything not involving x on the other. To do that, well, we've got two things that are equal. If we want to get all the x terms on one side, like I'd like this 3x to be represented on the other side so that all the x terms are on one side. Well, how can you do that? You've got two equal things. We'll do the same thing to both equal things, and those things will still remain equal. So if you want to get rid of a plus 3x, you could subtract 3x from both sides. The end result is, well, if you started with two equal things, subtracted 3x from both, you still have equal things. I mean, if you subtracted 3x from one side and 6x from the other, now you've thrown off equality. But do the same thing to equal things. You'll get equal things back in return. The 3x's will cancel, and we just have 4x minus 4 equals 8. Now, we've got all the x's on one side. I want everything else on the other side so that all I have is an x on the one side. Well, okay, we got to get rid of the minus 4. How do you undo minus 4? You undo minus 4 by addition of 4. But what you do to one side, you got to do to the other, else you'll throw off the equality. But having two equal things, adding 4 to both, you'll still get equal things. The 4's will cancel, and you'll get 4x equals 12. Now, how do we finish this off? Well, man, I wish x was by itself. It's not quite yet. But x is just being multiplied by 4. Well, if x is just being multiplied by 4, how do we undo multiplication by 4? Well, to undo multiplication by 4, we divide by 4. If we divide by 4 on one side and divide by 4 on the other, the equal things we started with will remain equal because we've done the same thing to both sides. We'll end up with x equals 3, and the problem is solved. Now, to validate that this is true, you could go back to the original form of the expression. Remember when we plugged in 0 and the equation didn't work, and we were like, maybe there's some x out there for which this equation works? Well, we've deduced, logically, that x equals 3 is the solution. And if you don't believe yourself, you could go back up to the original expression. Note that the left-hand side becomes 21 minus 4 when you plug in x equal to 3, and the right-hand side becomes 9 plus 8. Both of those are equal to 17, and indeed then, the two sides become equal when x is 3. Okay, in my final couple minutes, I want to describe to you like an example of a quadratic equation, but a simpler quadratic equation. I talked about something like this briefly last Friday, but the idea behind quadratic equations is going to relate to factoring. Because if you have a statement that something plus something equals 0, you don't have a lot of restriction, because 5 plus 5 minus 10 would be 0, or 10 plus 10 plus 20 or minus 20 would be 0, or 5 plus 10 minus 15 would be 0. There's infinitely many possibilities here. On the other hand, if you had something times something equal to 0, now that's so much more restrictive. Because if anything multiplies to be 0, one of the things being multiplied has to be 0. Because if the things being multiplied weren't 0, you wouldn't get 0 back whenever you do the multiplication. So much more restrictive, so much more helpful, because it reduces the number of possibilities. Additive statements equal to 0, Infinitely many possibilities. Multiplicative statements equal to 0. One of those factors has to be 0. That's huge. So to exploit that, in the case of a quadratic, let's try to solve for x. And let's look at the situation. X squared plus 5x equals 24. Now when you look at this expression, it's an additive statement. Additive statements more difficult to work with than multiplicative statements. That being said, if you had a multiplicative statement equal to 0, man, that's the best case scenario. So let's try to get to that situation. So if we got rid of the 24 from the right-hand side by subtracting it away, and of course doing to both sides, minus 24, on the right-hand side, we'd be at 0. And on the left-hand side, we'd have x squared plus 5x minus 24, which is still an additive statement. Wouldn't it be nice if we had a multiplicative statement? But can't we do that? If we just factored, we'd have a multiplicative statement. So let's do just that. So in order to factor this thing, we need two numbers. We need two numbers that add to 5 and multiply to minus 24. So as you think about factors that multiply to minus 24, let's see, what, minus 8 and 3? So 8 and 3 do multiply to be 24 and have a difference of 5 here, but they don't add to positive 5. Let's do 8 and minus 3. That will do it. So we'll take these two numbers, which add to 5, and multiply to minus 24, and take our middle term and rewrite it as two terms. We'll get x squared plus 8x minus 3x minus 24 equals 0. Now that we've got four terms, we group 2 by 2. Factor out the x in common from the first. Factor out the minus 3 in common from the second. Factor completely, we get x minus 3, x plus 8 equals 0. And those two things are being multiplied. And if two things multiply to be 0, what must be true? Well, one of them's got to be 0. The first would be 0 when? Well, x minus 3 is equal to 0 precisely when x equals 3. The second guy is equal to 0 when? Well, precisely when x equals minus 8. Once you take each of the factors and say, well, when are they 0? You can just take the factor, set it equal to 0, and solve. How do you get rid of the minus 3? You add 3 to both sides. Adding 3 to both sides, x is 3. I mean, just as well. You might have a simple enough expression here to where you can see that plugging in 3 for x would give you 3 minus 3, which would give you 0. Or plugging in minus 8 would give you x plus 8 equals 0. But I mean, worst case scenario, just take the darn factor, set it equal to 0, and solve. When is the factor 0? Well, when it solves to be 0. Interesting observation. When we dealt with the linear equation degree 1, we got one solution. When we had the degree 2 equation, we got two solutions. Maybe there's something to that. We can go into more detail on that as we sort of delve into more examples. But for this time, I sort of given you a little bit of a review about these things and a little bit of an introduction so that we can really get rolling with this discussion more about equations next time. I thank you for your attention. The sub here today, Jack, he'll be giving you your quizzes in a few moments after he answers any of your questions with the time that remains. I wish you all a good day, and I'll catch you guys on Wednesday.